Hi guys. So this week we're going to talk about regression. This is the last week of content for the course, of new content for the course. Next week we're going to review for the test, but we're also going to have a discussion about machine learning in the news. So I just want to remind you guys, if you haven't already, to find a news article that you can talk about and put it in the discussion forum. Follow the instructions there. And also to remind you, I mean, that activity, I think you'll want to be there in class because that activity will form the basis for a take-home exam question that we're going to give you next week, and that you can work on before the exam and bring to the test to hand in. Okay, so more information on that later, but that's just wanted to give you that reminder. So last week we looked at clustering, which was the first of two quick looks at non-classification machine learning. So in clustering, it was unsupervised. We didn't know, we don't have any labels that we know are the correct labels. We're just trying to put similar things together in a useful way. And that's the basis of recommender systems like Netflix and Amazon that push products at you that they think you'll like, or even Facebook with pushing its ads at you and stuff. They'll cluster you with other users with similar interests, and then use that to target you. It's kind of hard to construct a quick assignment like that, so we did the color quantization stuff, which I hope was fun for you guys. This week we're going to look at regression. So let's take a look at the handout here. Now you probably know this term regression. It comes from statistics, but in machine learning we apply it in a more broad way. So we're going to look at we're going to look at linear regression first. There are lots of statistical regressions you can do. Linear regression is one of them. Linear regression measures the correlation of two values, and also you can use it to, basically it forms a straight line model, and you can get a correlation out of it, and you can also get a measure of the error out of it as well. So that's linear regression. There are other statistical regressions as well, but you can also, it turns out, use some of the other machine learning tasks that we've used to do regression. So first of all, we're back to supervised learning. Okay, supervised learning meaning that we have targets, right? So in a classification task, the targets are labels, right? So my example down here, which we'll get to in a second, is about airfoil noise. So an airfoil is a wing, like on an airplane or a Formula One racing car or something like that. And as the air rushes over it, it makes a certain amount of noise depending on a whole pile of different factors. So in this case, we have a training set which consists of, here, let's take a look at it, consists of a bunch of measurements of an airfoil. And here's a picture that shows you maybe what some of them mean, frequency, angle of attack, and so on. If this was a classification task, we might be classifying different airfoils as noisy or quiet. So the targets out here would be just labels, 0 or 1, or noisy or quiet, or maybe several levels of sound. But in a regression task, we're predicting a number. Okay, so anytime you want to have a target number that you're trying to predict, then the task is no longer classification; it's now regression in the world of machine learning. So it's still supervised. So we have a training set and we have a test set. We have the correct answers that we can give the system when we're training it, and we use those correct answers on the test set to measure how well it does. But things just look a little bit different in the measurement. We can't just do an accuracy measurement. What we have to do is do some kind of measure of total error. And also, that's where the correlation comes in. We can do a correlational measurement between the correct answers and the answers given by our system. Okay, so in regression, the outputs are numbers rather than discrete labels. That's the main difference. Now, so we'll take a look at linear regression, and we'll get you to do that. It's built into sklearn, and we'll get you to do it in the assignment. But the way a linear regression works is that you have a prediction. So your predicted sound level here in this example, you get it by a linear combination of the features. So each one's going to have a coefficient. So 0.002 times the frequency, plus 3.637 times the angle of attack, plus 186.7 times the chord length, and so on and so on and so on. These are the coefficients. So the coefficients that the system has learned from the training data are 0.002, 3.67, et cetera, all the way up to negative 557.017. Those are its coefficients, and there's an intercept as well. So like any linear equation, there's an intercept that just moves the thing up and down. It's not a multiplier on one of the terms. And this is the equation of a straight line. In this case, it's a straight line in in six-dimensional space. That's why we call this a linear regression. There are other kinds of regressions that aren't straight lines, but this is the most common and the simplest to understand. Okay, so these are the coefficients here. Oh yeah, so here's the coefficients, and here's the constant term or the intercept, and then here's a new example, right, with values for all those different features. And we just plug those into the equation. We multiply each feature by its coefficient, add them all up, add the intercept term, which is negative, onto the end, and this is our prediction. So that's the predicted sound level. Okay, so here's an example. Here's what a linear regression looks like in 2 dimensions. It's just going to look like a straight line. So this is pretty nice data here, but it's always a little bit noisy, so the data falls but on either side of the line that we've drawn. But on the whole, you can see that it trends upwards. There is a linear relationship between whatever this number means and whatever this number means. In fact, here's the equation of the line that's drawn between them. So here it is with the data, and here is just the line. So this is what the line looks like. We want to make a prediction. Basically, we have one feature here, by the way. This isn't like a classification task where we have 2 features. We have one feature down here, and this is our prediction. And we end up with a line in 2 dimensions. So if our feature value is 0.5, the prediction, we just read it off the line, is 3.84. Or if we're to do it mathematically, we just take our single feature x, plug it into this equation. If we had 2 features, we'd end up with a line in 3 dimensions, because we're trying to predict, we would have x and y, and we would be trying to predict z. So we would have a 3-dimensional line, and we would plug in x and y to try and get z. Okay, and in 6 dimensions, it's no longer visualizable, but the basic idea is still the same. Okay, now this can be done, by the way, with a method called ordinary least squares. Just statistical methods, well understood statistical methods that get us a line while minimizing the overall amount of error. So when we measure performance, there are a couple of things that we can do. We measure the performance of our algorithm. So we take its performance on the test data and we compare it to what the correct answers should have been on the test data. One thing we can do is we can compute the correlation coefficient, which is a measurement of how well our test values, our predictions, match the target values. It's a measure of how well our predictions track the target values. So correlation coefficient goes between -1 and 1. What we're trying to do is, what we hope is it gets close to 1. So as the target value goes up, our estimates go up, and as the target value goes down, our estimates go down. It doesn't tell you everything though, but you can use it to know whether you're really getting, to give you a sense of whether you're really getting any kind of traction on this task. If the correlation is negative or is close to 0, then your learner did not do very well with this task, and maybe you should try some other method of regression, because linear regression isn't doing very well, no matter what the other sums of errors are telling you. Okay, so you want it to be high. You want it to be like close to 1 if possible. In practice, if you're at 0.5 or higher, you're probably doing really well. So then the other thing you can measure is sort of an overall estimate of the error, which is called the residual sum of squares. So the correlation coefficient can tell you whether you're kind of on the right track, whether your model is behaving the right way, going up when the real values go up and down when the real values go down. But you use residual sum of squares to estimate the total amount of error. So go back to our model here. Here's our one-dimensional data and the model. If a new point comes in, a test point, which is here, our model is going to predict this value here. The difference is the residual. So we predicted 3.67. The correct answer was apparently 4. So the residual is negative 0.33. We were 0.33 too low. And then down here, we'll say that the correct answer was 3, but we predicted 3.33. So we're off. Our residual is in the other direction, is 0.33. We were 0.33 too high here. So those are the residuals. So you do that for all your testing points, and then you do the sum of the squares of the residuals. You square them for a couple of reasons. One reason is if we didn't square these residuals or do something about this, they would cancel out. So the residuals up here would cancel the ones below here, and you could end up with a line that's way off but has a low estimate of error because your positives are canceling out your negatives. So one of the things that squaring does is it makes everything positive. So now whether the residual is above or below the line, we are still adding to the error, the total error count. The other thing that squaring does is it emphasizes things that are far from the line. So if you have one point that's way out, it's going to add a lot of squared residual error, whereas things that are close will add just a little bit of error. So that's called the RSS error. In this case, it's 0.33 squared plus negative 0.33 squared. So our total residual error is 0.218. Again, just like when we did this with clustering, you can't use residual sum of squares error as an absolute measure of how good your system is. Because if your feature values are high, the distances are going to be bigger and the residual sums of squares are going to be higher. Or not if your feature values are high, but if there's a lot of spread in your feature values, it's going to exaggerate it. And also, I mean, closer to 0 is better. But if you have a lot of points as well, so if you have a data set that's twice as big as somebody else's, you're going to be adding the residuals for twice as many points. So on its own, the residual sum of squares error doesn't really tell you very much, but you can use it to compare other regressors. So if you get a residual sum of squares error of 1,000 for your linear regression, then you do a different regression, maybe a parametric regression or something like that, and you get an error, some squared error on the same data of 500, then that's half the linear one, so it's doing better. Okay, and again, you can't trust. Correlation is good to look at, but you can't trust it. So here's some data here. These are the predictions and these are the targets. This would never happen. It's just something to prove my point, to illustrate a point. If you notice, I think each value is off by, is it 67 or 57? The residual error, it says for each of the values is 67, but actually this one is only 57, so that might be a mistake. But the rest of them I think are 67. So it tracks the up and down perfectly. So I was off here, but now the value goes down, so does mine. Now it goes up, so does mine. Now down, so does mine. So my targets are tracking, these are my predictions here. My predictions go down when the targets go down and go up when the targets go up. So it's tracking it really well. And in fact, it has a perfect correlation, or near perfect. I may have gotten this point wrong, but a near perfect correlation of 1. But the individual values are still way off. So the RSS error is going to be 67 for each of them, squared, added up, which gives us 35,912. So the correlation on its own doesn't tell you anything, except whether you're kind of on the right track or not, but it doesn't tell you how well you're doing, really. And the RSS error also is a comparative error. You can't tell much by looking at the absolute number. You have to use it as a comparator. So a linear regression model is computed using a method called ordinary least squares, which is where you'll find the linear regression class in sklearn. Okay, and we'll go over that code in just a second. All right, so I hope that was fairly clear. There are some examples here, some exercises, which I'm going to leave you guys to do. I'm going to keep this video going, but I would like you to try these exercises. You might even want to pause it now and try them, and we'll take them up in class. But here you've got some example data. So it says, consider a regression task with 2 features. Your linear regression model has assigned these weights, 3.07 and negative 2.05, and has an intercept of 1. So use that to make predictions for this previously unseen data. So come up with predictions here, and then I give you the actual targets, and I want you to compute the RSS error. And you can also compute the correlation as well. You can do it in Excel. I show you how to do it here. So, and then look at the R and the RSS and see if you can come up with something intelligent to say about how well your model is doing. Okay? So I'll leave that. We'll take that up next class. And maybe, you know what, maybe we should take a quick look at the code for this week as well. So here's this week's code. I have, what is this? I have a CSV file here with the airfoil data that I drew my examples from. This comes out of a machine learning textbook that I used to use. So the numbers are what I say, and the last column, what I say in the handout, and the last column gives you the target values for them. So in here, I open it up. I split it into 75% training and 25% testing. So I read in the airfoil file, split it up into training and testing. And here's the line that gets me the linear regression class from sklearn. It's in the linear model class. And it's just fit and predict again. So rgr.fit fits the data using the training data, and rgr predict on the test data gets me my predictions. So if I run this, I have a few outputs here. We'll go into them in a second. Just let it run. So I'm computing a correlation here of 0.73, which is pretty good, and a residual sum of squares of 8,555. And each time I do it, I should get a slightly different set of data. These are the coefficients for the linear regression here. Okay, and they're in scientific notation. So this one's 0.001, negative 0.001. This one's negative 0.3, and so on. And this is the intercept. Now the regression model, I stored it in a variable called RGR. So if you go RGR predict, everything here is a global variable. So I can go test data. This is what I get. These are the predictions from the model. And the correct answers are, I believe it's test targets. Oops. So we can compare them. So the targets, let's look at the last four. 120, 133, 131, 130. I predicted 124. That's off by 3. So you can see they're a little bit off, but they're in the right ballpark here. And the correlation that I measured was 0.73, so it's not bad. And the residual squared error is what it is, 8,500. Once I've trained the regression model, I can get the coefficients like this. So that's the multiplier on each one. And I can get the intercept like this. So I could actually do these calculations myself, but it's easier to just go predict. And then here's where I'm computing the residual sum of squares. It's just the predictions minus the test targets squared. And then I just sum that up. That's my residual sum of squares error. Not test data, test targets. There we go. That's my residual sum of squared error. And there is this correlation coefficient method here, like this. If I run this, I actually get a matrix. This is in case you can call this correlation coefficient method with multiple variables, and then it will show you the correlations between each pair of variables. So this is, prediction, this is test targets, and then on the rows, this is prediction and test targets. So it's showing me that prediction is correlated perfectly with itself, and test targets is correlated perfectly with itself. But either of these numbers is the correlation between prediction and test targets. Okay, so if I had more values, there would be a bigger matrix than this, but the line through the diagonal here would always be 1. So what I've done in the code is I just pulled out one of those values as the actual correlation coefficient. So you can get the correlation coefficient that way for all your regression models. Okay, so pretty straightforward. You can look up, there's not much to do really with the regression model. There aren't very many variables. But if we take a look in here at, oh, I don't have it open yet. I'm gonna have to leave the student view to go take a look at it. Here we go, week 12 regression. Here it is. So here's the linear regression, linear regressor right here. You can see there aren't very many parameters here. You can, oh, I guess you can choose to normalize the data before you do this, and you can choose to use an intercept or not, or have an intercept of 0, I guess. So, I mean, there's not much to do. Just run the linear regression and see how it does. But it turns out that a lot of our classification systems can also be used as regression systems. So you can find, again, if you go here, back to the links, you can use, of the ones we looked at, you can use, where are we? Here we are. Nope, not there. Here. You can use KNN, decision trees, and multi-layer perceptrons also as regressors. So, for example, you go to K-neighbors regressor here. So this is how you would import it. From sklearn.neighbors, import K-neighbors regressor. And it has a lot of the same parameters. N neighbors, that's the K, and so on. So I'll let you guys take a look at this yourself, and for decision trees as well. But basically, in KNN, there's no training phase. When you classify, you just compute the distance between a new example and all the training examples. You find the K nearest ones, and they vote. In KNN regression, you're predicting a value, so get those K neighbors the same way, the nearest neighbors, and you can just compute the average of their value, of their target, and return that as your regression. Okay, so so you weight the contribute. So you just get the average of the neighbors, and you can also use a weighted average, where you weight the contribution of each neighbor to the average using the inverse of its distance. So more distant neighbors have a smaller effect on the prediction. You can use decision trees. When you use a classifier, you assign a label using the majority of label examples in a leaf node. A regressor assigns a value based on the mean value of the training examples in the leaf node. So yeah, and when learning, it chooses splits based on minimizing the mean squared error of the split. So the average squared difference between each example and the mean on that side of the split. So it's just small tweaks, and you can use the same algorithms as regressors. Multi-layer perceptron, basically you can train it like you normally would, but you use, at the output node, you don't have an activation function. It's just the identity function, f at x equals x. It just passes through the total activation level. You can use ReLU or tanh for the interior nodes. It's the same other than that. Okay, but you're just outputting, instead of a value between 0 and 1 or whatever, or -1 and +1, you're just outputting an arbitrarily valued value. And believe it or not, just the same algorithm just works just fine for that. So maybe I'll just show you real quick here. Let's use KNN. sklearn neighbors, K-neighbors regressor. So let me save this first. Save it on the desktop as regression. sklearn.neighbors. Import K, gotta spell this right, neighbors regressor. Is it? Do they use the Canadian or the American? Yeah, the American spelling, of course. K neighbors regressor. Then we just change this here for that one. We need to give it a parameter though. Oh, we don't actually. I think it's got, yeah, by default it's going to use 5. So let's use 5. Save that. I think this will work. See how it does. Remember we got, oh, I need the airfoil file. Copy that, put it on the desktop. There it goes. So we got 0.73 regression. Oh, it doesn't have the, of course, it doesn't have this, because it doesn't do the same kind of job. It doesn't have this coef and intercept. The rest should work though, I think. There we go. Oh, it didn't do as well as my linear regression. Probably because this data is meant to do well with linear regression. So for k equals 5 anyway, I got 0.5 and 13,000 as opposed to 0.7 and 8,000 from the linear regressor. I could try messing around with some of the parameters. What if we just said n neighbors equals 1? American spelling. Would that help? Nope. How about 3? All right, in that case, how about 20? Nope, that doesn't help very much either. So anyway, you can mess around with it and see what you get. Uniform weights are used by default. So let's try weighting by distance, like I said. So let's go weights equals distance. I think that's how you do it. Made it worse. Okay. And so anyways, I don't know why I'm acting embarrassed. You know, it is what it is, right? But I guess I kind of expected K nearest neighbor without having tried it before this video. I kind of expected it to do better than this, but it ain't. That's fine. So interesting. Anyway, so what I want you to do in the assignment is you're going to look up. You're going to find a data set on the UCI machine learning repository. I want you to do a linear regression, and I also want you to try one of these other regressors as well. And you can mess around with the parameters. They're similar. You'll recognize them. They're similar to what you've seen for classification. Let's take a quick look at the assignment. I think this link is broken. We want multivariate regression. Don't use the airfoil set or any other set we looked at in class. If we click here, yeah, I'm going to fix this link. But you want view all data sets. You want regression, and I think you want multivariate regression. Yeah, so we want numerical data as always, multivariate regression, and these ones should be good as long as it says regression here. Again, you just read it carefully and make sure that it really is suitable for regression, that the targets are numbers, especially if it says regression and classification. So try some of that. And I don't think I put in any requirements there about how big the data set is. Yeah, it says you can use basically any set you want. And you're going to test different kinds of linear regression? No, different kinds of regression. I'll fix that too. So load the data set, split it into test and training, output the size of the test and training sets and the number of features. Output the error, correlation, weights, and intercept for a linear regression, and then output the error and the correlation for one other regression technique. That's pretty limited. I mean, it shouldn't be hard for you to try several, so feel free to try several. But what I do want you to do is experiment a little bit more than I did beforehand to try and find parameters that are going to show off the best achievable error rate for this other regression technique. So don't just give it the default parameters. Try and find the best. Mess around with a bunch of them to try and find the best one. In the comments at the top of your code, state which algorithm performed the best and offer at least one reason why you think it performed better than the other. Okay, so no report for this, just a comment at the top of your code telling me which one's better and why do you think it was better. Give me a good reason why you think it might be better. Okay, that's it. So I will fix this link and upload a new version of this assignment. But other than that, that's it. We will go over this stuff in class, yeah, maybe talk about the test and stuff like that as well. Okay, so any questions, let me know. Otherwise, I'll see you in class.